So hello everyone, I'm Tomasz Żyjewski and the topic of this presentation is getting started with the meta-selinux, enhancing system security on QEMU. Here is an agenda of this presentation. First, I will introduce myself and the company I work in. Next, I will try to describe what Selinux is, briefly present its history and the most important features. Later, I will tell how this control system should work, which will allow me to delve into its individual elements and talk about access control mechanism and policies. This set of knowledge, I believe, should be sufficient for a basic understanding of the topic. Next, I will move on to the meta-selinux overview, and I will try to describe the metadata provided there. And I will finish the presentation with a description of running core-image-selinux on QEMU. And maybe we'll be able to create some custom models, security models for our image. Oh, maybe I'll just a little, oh, okay, that would be better, I think. Okay, so here's something about me. I am an embedded systems engineer at FreeNDep. I'm working here for over 2 years, during which I gained knowledge related to Yocto. I have quite a lot of experience in integrating update systems, mostly based on SW update. I also enjoy working on improving platforms boot times by optimizing the kernel or bootloader. If you would like to contact me, you can use an email listed here or just hit me on Twitter. I would also like to introduce the company I came from. FreeNDep is embedded system consulting company. We are based in Gdańsk, Poland. One of our main goals is to promote open source solutions by using them on firmware and the systems we work on, because we strongly believe that following the path of open source increases the security of the devices around us in today's world, and thus also our security. Okay, so let's get with the topic. The security enhanced Linux is a Linux kernel security model that provides a mechanism for supporting access control security policies, including mandatory access controls. We can take S from security and E from enhanced to see from where the Linux name comes from. Its correct implementation in the system significantly facilitates the control for the system administrators. And in practice, the kernel queries the Selinux before each system call to know whether the process is authorized to do the given operation. Work on Selinux was started, I believe, by the United States National Security Agency, which provided a series of kernel patches using the Linux security models framework. The first release was made available to the community in the 2000s. In the form of patches I mentioned before, and that they were finally integrated into the Linux upstream 3 years later. Of course, this project is still supported. At the time of this presentation, the latest version available is the version 3.3.0, which was released on October 22nd this year. I believe new versions are delivered quite regularly. In the course of the last few releases, it can be said that new versions appear after every 6 or 7 months. The Selinux also implements the Flask, which is an operating system secure architecture that provides flexible support for many kinds of mandatory access control policies. Okay, so in case of Linux system security, we can talk about modified versus unmodified system. The security of an unmodified Linux system, so the system without the Selinux, depends on the correctness of the kernel, of all the privileged applications and each of their configuration. So one fault in any of these areas may allow the compromise of the entire system. In contrast, the security of a modified system, so the one based on the Linux kernel, depends primarily on the correctness of the kernel and its security policy configuration. While problems with the correctness or configuration of application may allow the limited compromise of individual user programs and system daemons, they do not necessarily pose a threat to the security of other user programs and system daemons or to the security of the system as a whole. The Selinux is highly configurable and provides a hybrid of concepts and capabilities borrowed from the many forms of access control available. The third-party tools allow to create various security policies. The discrete security system, the Selinux, can be implemented without any problems in many Linux distributions. In the links provided on the slide, we can see that there are available packages for the Arch Linux, for the Alpine Linux, Ubuntu, and the build systems like Buildroot or Yocto project. Linux provides a set of features, among which you can mention like the clean separation of policy from enforcement, flexible policies. Policies consist of modules which facilitate the creation of custom ones. Well-defined policy interfaces. The interfaces are like the set of public functions that other modules can use to properly interact with new modules. Well-written rules allow to control practically everything that is part of the system. So we can control the processes, files, folders, sockets, and the others. And the last feature I want to mention is the default deny policy, which means that any attempts to access processes, files, etc. that are not described by the rules are automatically blocked. Okay, so how it works on the running operation system. When starting the system, the selected policy is loaded, which is a set of access control rules. From this point on, we can distinguish between the subjects and objects. The first group includes applications or processes, and the second, for example, files. When a subject makes a request to access an object, the Selinux checks via the access vector cache, the FEC, whether the operation can be performed or should be blocked. Sorry. Okay, so the all access denials are recorded in the system logs. By default, they should be available in the under the var log.messages file. These messages may be difficult to read, but they have a structure that can be discussed based on the log I provide on this slide. So first we have the FFC denied. This is the type of the log. So the first one is the type of the log. So in case this is the FEC log, and the second one is the state, which can be denied or granted, depending on what the Selinux has done with the access attempt. In this case, it is denied. Then we have information about the subject that triggered the check, and this is the systemd fstab G process, whose speed was 447. We also have a security context defined here for both the process, so the S context, and for the resource it tried to use, so the T context from the target context. In the curly brackets, we have the indicated permission required by the given process. In this case, it was the DAC under DAC underscore override, which purpose is to bypass file read, write, and execute permission checks. The following diagram sums up the process performed by Selinux each time an attempt is made to use a resource. So you can see that the subject tries to access the object, and the Selinux server starts checking if there are some rules for that subject right under the Selinux policies, and check if it checks if the permission can be granted. If yes, then the subject can use the object it wanted, and if no, then we should see the FEC denied message like the one that is here above that diagram. Okay, so the type enforcement and labeling are the most important concepts for C-Linux. The labeling means that every part of the system has a label associated with them, and the labels are a logical way to grouping things together. The format of labels are user, role, type, level. So in the provided FAC log, we have here a user and role, the system, and the type is systemd generator, and the level is S0. Later I will talk a little bit more about the labels itself. And the Linux uses also type enforcement to enforce a policy that is defined on the system. Okay, so Linux can use many kinds of access control mechanism, but mostly targeted policy and multi-level security is used. The first option is much less complicated, based mainly on the types read from the labels. The MLS also uses the user and assignment roles. The ACM'S is also something I will come back to later. Okay, but there are several ways to read the Linux configuration that is implemented on our system. I represented the three of them. We can read information from the configuration files stored in etc/selinux config, from which we can check which mode Selinux is currently working in and which policy is the system using. I have not talked about the modes before, so as we can see in the comments of this configuration file, Linux can run in one of the three modes, the enforcing, permissive, and disabled mode. The first one means that all the rules listed in a given policy are enforced. So maybe when we are trying to first time to implement the Linux on a new system, it is worth running it in the permissive mode, where instead of blocking access like in an enforcing mode, the Linux only prints warning in logs, giving us information about what would be blocked when the Linux would run in the enforcing mode. This approach allows us to fine-tune the set of rules needed for the system to work correctly. And the last mode is actually the last mode, so the disabled mode is just actually for turning the Linux off. Okay, so the second way to check the Linux configuration is to check the Linux server file system, which is mounted during the boot, and it contains commands that are used by kernel subsystem. It works in a similar way that the prot server file system. From it, we can for example use cat command on the enforce file to check if the Linux is currently running in the enforcing mode or the permissive mode. And the last way to get the configuration of Linux on running system is to use the CS status tool, which is by far the most informative way to get the Linux configuration. It is one of the many command line utilities that are available after installing the Linux on our system. Here we have information about the current operating mode of the system and what is defined in the configuration files, because the mode can also be changed at runtime. And in addition, we immediately get information about the loaded policy or the path under which the server file system is mounted and where the files related to Linux are located. Now we can dive a little deeper into the components that make Linux. I would like to devote the next few slides to a description of several access control mechanisms and policies. The task of ACM is to make it easier for system administrators to get local control over any process, user, and their access to resources. The very basic access control is defined by discretionary access control. In this approach, it is the owner of a given file or device that decides whether another process or user can access it. The ACL introduced an extension to this standard permission system because those standard systems allow only to set permissions for the owner of a given file, the group to which the file belongs, and the third group is the others. And the ACLs allows to set permissions to files for any kind of user or group. Next, we have the mandatory access control, which approaches control access in a completely different way. Contrary to the previous ones, the owner of the file does not necessarily have full access to it. The Mac introduced additional labels that determine the accessibility. I'm sorry. Next, we have the role-based access control, so RBAC, which takes a different approach to access control by using roles that are assigned to users. Unlike DAC or Mac, in this case, user and resource permissions do not count. We have also the MLS, which is a specific version of mandatory access control. This is related to the division of the system and processes taking place on it into several security levels. Then appropriate relations between these levels are assumed, which is referred to as the no-read-up and no-read-down model. And we also have an MCS, which is an extension of Linux that allows for labeling files with categories. So now I will talk a little bit more about the DAC and Mac mechanism. Okay, because they will show the main differences between the modified versus the unmodified Linux system. This slide shows the relationship between the user and objects in the system. As we can see, a given object has full access to its owner and the group to which it belongs. It is also worth paying attention to the role of the root user. In this access control mechanism, there is a root user that has access to all files, processes, and sockets included in the system. Here is an example of the mandatory access control. Access to objects is determined based on the rules set out in the policies. It can be stated that it works above the DAC because it does not base permits only on the basis of which user is the owner of a given object. There's also no root user concept here, so it is not possible to switch to a special account or something like that to obtain some more permissions. This diagram shows actually the MLS and thus an even more secure version of Mac. We can see here that subject that is at a higher level of security has access to the files at a lower level, but this relation does not work the other way around. Okay, so now we can talk a little bit more about the policies itself. As mentioned before, they are a group of rules which Linux uses to manage access control. Rules define file types and domains for processes running on the system, and they use rules to restrict access to predefined domains. Types in Linux are used to group items based on their similarity from a security perspective. In this case, it does not matter what is inside the file or what is the purpose of it. For example, if it belongs to a given user and is in the user's home folder, it's assumed that the file will have the home_user_t type, just like the rest of the files in the same location. This means that from the security point of view, these files will be handled in the same way. The policy itself on this running system can be found under the etc/selinux path, and it is a binary file. It is loaded by the kernel when the system boots. Okay, so now I will talk about a booting system with the Selinux enabled. So Selinux plays an important role right from the start of the platform's boot process, because even then it can detect some problems with access permissions and block something we do not want to happen. Therefore, the init program needs to perform a set of actions to ensure that all elements that make up the system receive the appropriate label before we apply the selected policy for the system. So after the kernel is loaded, the initialization process is assigned with the initial Selinux ID, which is used during the bootstrapping before the policy is loaded. After the init process mount the prod subsystem, it searches for the Selinux pseudo file system. If it is present, that this tells the kernel that the Selinux will be enabled on the system. Next, the init looks which Selinux mode is set, so if it is the enforcing, permissive, or disabled mode. Later, the write policy is loaded using the binary file stored under the etc Selinux path. At this stage, after this policy is correctly loaded, we can say that Selinux is fully prepared and kernel can now retrieve security context from in-kernel security server. So in the next step, the init program only re-executes itself so it can transition to a different domain if loaded policy defines it, sorry. And later the normal boot is proceeded. Okay, so the most basic policy in Selinux seems to be targeted policy, inside which all undefined subject and objects are automatically assigned to the unconfined_t domain. This means that they have no additional restriction and use the TLC for security. And this type of policy, a couple of daemons runs in their own domains like HTTP or NTP, which runs in HTTP_T and NTP_T domains. After implementing the Selinux, the ls command has the new additional flag, which is Z, and it can be used to check the labels assigned to given objects. Okay, so now I can go to the overview of this meta-selinux layer. So the code is available on the official Yocto repositories. Link is shown on the slide. It looks like this. It looks like it can be used with any of the Yocto releases because there are branches for any of them, and it can also be said that it is relatively stable and updated because considering the number of contributors from the last year. Okay, so in the repository we can find a very well prepared README file which clearly presents the information needed to build an image with Selinux enabled. To prepare that build configuration, following steps needs to be done. So we need to add the ACLX, PAM, and Selinux to these two features. Set a policy which we want to be run on the system, like here is the ref policy NOS, and set the version of this policy. Additionally, we get information about the default init manager used in the distribution, which is the sysvinit, and an additional instruction is included on how to change it to systemd. And also can say that the meta-selinux provides two build targets. The one is the core-image-selinux and the other is core-image-selinux minimal. From what I can say is that the minimal version do not automatically relabel files after the boot of the system, which needs to be done manually when we use the minimal image. So okay, later then we have the BB classes files. Most of those classes allow to prepare the appropriate configuration of the build packages with the Selinux support. They add an appropriate entry to the package config variable. We also have a Selinux image BB class here that introduces a function to perform file labeling on the root file system, and there is also an enable audit BB class that adds audit to images using Selinux. An audit is a framework that is responsible for writing the messages that were generated through the audit kernel interface and triggered by application and system activity. So the APC messages that was presented before are printed this way. Okay, so the vast majority of files in the meta-selinux layer are the BB-appends files, which just enable the selinux on the given package. In addition to this, we also find the recipes for reference policies. We have here the Git file, which has the source reset. From what we can see that the ref policies are get from the GitHub repository. And also we have the common include file, which is responsible for compiling the policies and installing them on the target system. It has almost 100 patches, which need to be done, which need to be applied, which are necessary to apply it for the Yocto-based distributions. Okay, and the rest are the set of recipes that are strongly Selinux dependent. So they provide some API to communicate with the binary policy, or provide a set of command line utilities which can be used later on the system, like sysstatus, etc. Okay, so now we can move on to trying to build the system and run it on QEMU. Fortunately, the instruction given in the README meta-selinux repository proved to be sufficient, making building the image quite easy. Being a big fan of a cast tool, I use it to prepare the build configuration. We need to set a couple of variables mentioned earlier and use the following layers presented on the slide. So there are some layers from Poky, some layers from Meta Open Embedded, and the meta-selinux itself. For the machine, I use the core-image-selinux, and for distro Poky. Out of curiosity, I also measured the time to prepare this, needed to prepare this image, and on a computer with a CPU with 8 cores, it took less than 277 minutes. Okay, so after the build was finished, I was able to start the QEMU image. I run it with sleep serial stdio flags to have user networking without root privileges and serial console on the terminal. After booting the system, we can perform a series of checks to make sure Selinux is loaded. So first, you can check the output of the sysstatus command. You can see that we are currently in enforcing mode with a targeted policy and loaded, and we can also view the system logs, from which we can see that practically at the very start of booting the system, the Selinux initialization takes place, and we can also find here a note about performing the auto-relabeling. Now we can look at the system logs for access denials. As you can see in the attached slide, it's quite easy to find few refusals. As the system now operates on targeted policy, processes operate in unconfined domains. Fortunately, the system used here does not have any additional complications, so the system managed to boot, and the problems shown here are not critical. In the past, we have worked with the system in which the Selinux implementations prevent made the platform just unbootable, so we were not able to start it at all. At times like this, the permissive mode came in handy, because then we can boot the platform and just work with the denials we get. And when working with denials, the audit to allow utility might be helpful. In my opinion, it's one of the best tools available on Selinux system to help with working with access denials. The result of the help is shown in the slide. This tool allows to list all messages generated by an audit from DMESC, from the last boot, on from the last or from the whole last audit log. It can also clearly explain what a given refusal means when we use the W flag. And most importantly, it allows us to generate models that can be used to prepare model files that can be later prepared inside the Yocto build system. Okay, on the slide you can see the output from the audit to allow with an additional W flag, which I talk about. From such looking, okay, so from the logs which are looking like this, we can read more. And they are more transparent. What's more, the program itself tells us if we are able to prepare a model that would remove a given access problem. As an example, we try to execute the ping command as it were working on the normal system. After adding Selinux, we see that there is some permission denied issue. We can now investigate the audit messages using audit to allow. Next, we can try and use the large aim flag to create loadable model to grant permission for ping command, and will not be loading this model on time, but will use the generated files in the Yocto build. Okay, so we also get the TE file, which is the type enforcement file, and it is presented here on the presentation. It consists of allow commands, which we are missing now to successfully run ping commands. Every module also needs file context and interface file to be compiled, so we also create those. They can be just blank files. They are needed just to compile the module while we are building the image in the Yocto. The module compilation self function is described in the file ref policy command that I mentioned earlier. So our task now is to deliver the source code for the new model before this compilation happens. So yeah, we just added those to the ref policy target and rebuild the image. Okay, so after rebuilding the image and start it again, we can see that models go to the user share Selinux by default. So this confirms that our model was added and the compilation was ended with success. Now let's try to use the ping command, and as we can see, we no longer get access denied errors, and the command is successfully executed, which means that our model is added to the policy we currently run on the system. And as a summary, the Selinux provides an additional layer of the system security. It fundamentally answers the questions It fundamentally answers the questions if the subjects can do something with the object, like for example, may a web server access files in users' home directories. Each of such questions can be described in the Selinux with an appropriate rule, all thanks to the ability to add your own configurations. The Selinux itself is definitely more complicated than what I tried to present here, but I thought that it was worth giving so many theory to understand what we are dealing with there. And to get the most of Selinux, one definitely need to spend a lot of time reading the documentation. And the meta-selinux described here is easy to integrate with our own build, but when planning the system architecture, it is worth considering at the very beginning whether the Selinux should be integrated there. Attempting to add it at the later stages where the system can be much more complicated may fail. When we work with Selinux from the beginning, using the audit to allow tool may help to easily add new rules to a custom policy. And that's it for this presentation. We as 3ndEP are open to cooperate and discuss, so feel free to contact us if you believe we can help you in any way.